Alright, chemistry, this is your video lecture for chapter 7, section 4. We are now going to be determining chemical formulas. Earlier in the chapter, we simply learned how to describe chemicals using their formulas. Now we're going to be able to figure them out based on empirical data. And we say empirical data in industry, in real cutting-edge chemistry, analysis of some sort of chemical is done through various means. One of the common ways that you may see if you take chemistry in college is through an NMR machine, and what that spits out, well, among some other things, is the percent composition of whatever chemical you put into that machine. And so last section we discovered what percentage composition is, how to determine that. Now when you use this sort of physical analysis, you're given percent composition, and we're going to learn what to do with that percent composition in this section. So, section 4, objectives. Define empirical formula and explain how the term applies to ionic and molecular compounds. Then, determine an empirical formula from either a percentage or a mass composition. Again, this is where we're going to use what we learned last section, the percent composition, and turn that into a formula, an empirical formula. Mass composition, again, you'll actually simply use that, you'll turn that into a percent composition and then use the exact same procedure. Explain the relationship between the empirical formula and the molecular formula of a given compound. So once you establish the empirical formula or are given the empirical formula, you should be able to figure out the molecular formula. And then lastly, determine a molecular formula from an empirical formula. Here we go. So let's start by establishing the empirical formula. There are a few things that you need to do in order first. You're going to base any of your calculations on the assumption that you have 100 grams of the formula. You are going to determine the moles of each element in 100 grams of that compound. You're going to divide each value of moles that you just calculated by the smallest of all the values of the moles. And 4, multiply each number by an integer, meaning a whole number, to obtain all whole numbers. Okay, so we'll go through a couple of different examples, and this is going to be a very example-heavy lecture, because the idea here is not that complicated. We're actually doing very basic, simple math. The only thing that you need to understand is what an empirical formula is, and it is the smallest whole number ratio of all of the elements involved in that compound, the smallest whole number ratio. All right, so part 1. So we have a particular type of acid, adipic acid, and that contains 49.32% carbon, 43.84% oxygen, and 6.85% hydrogen by mass. Okay, again, percent composition. What is the empirical formula of adipic acid? So first thing I want to do is convert this into a gram. Okay, a gram. Notice that I've been given percentages, and the first term that I have here in my conversion factor is grams. This is what we get to do when we assume a 100-gram sample. Remember that on that last slide, assume a 100-gram sample? Because if we do have a 100-gram sample, 49.32% of a 100-gram sample is in fact 49.32 grams. 43.84% oxygen of a 100-gram sample is 43.84 grams. And so this allows us a very convenient way to turn that percentage into a gram. And I'm simply going to convert this gram value, using a regular old conversion factor based on the molar mass of that substance, of that element. Here it's carbon. We're going to determine this is 4.107 moles of carbon. We're going to do the same for each of the other two elements present in this compound. Now that we have carried out all these calculations, we have 3 values whose units are in moles of that element. Okay, we converted grams of carbon to moles of carbon, grams of hydrogen to moles of hydrogen, grams of oxygen to moles of oxygen. So we have 3 values of moles. as we move on to part 2, we're going to be using these values for moles, but this is where we get them. Converting the percentage into a gram value and converting that gram value into a mole value. Let's move on to part 2. We're going to divide each value of moles by the smallest of the values. So we looked at carbon, it was 4.07, 4.107, hydrogen is 6.78, oxygen was coming in at 2.74. So we're actually going to divide each of those values by the smallest, which in this case is oxygen's 2.74. So we're going to divide them all out, and it's going to give us a decimal. It's going to be a decimal because there's no units. Notice that I'm dividing moles and moles, moles and moles. It's just a ratio between these two types of elements. So for carbon to oxygen, it's a 1.50. For hydrogen to oxygen, it's 2.47. And obviously for oxygen to oxygen, it's 1. So I'm going to take these 3 values, and I'm going to use these in the next step. Okay, so this is where I'm getting these values, these small values that are based on moles divided by moles, always dividing by the smallest molar value. Then I'm going to multiply each number by an integer to obtain whole numbers. Now here's the thing. Starting off, I do not know what that integer is. I'm going to have to do a little bit of guess and check. And as you guys do more and more practice, this will get easier. But I'm essentially going to do guess and check until I get whole numbers for all 3 values. So carbon coming at 1.50, hydrogen 2.50, and oxygen at 1.00. For those of you who are looking at this going, wait a minute, on the last slide, hydrogen, that ratio is 2.47. Now, that's true, but remember, we're being limited by the number of significant figures here, and so the exactness is a little bit off. If we were to use infinite significant figures, that would actually come out to be 2.50. And so what that means for you guys, functionally, when you're working out these problems, if you get a value that is, like 5/100ths off of being one of these nice round numbers, and the numbers that you're going to use here are mostly whole numbers, halves, quarters, and thirds. Right? Sometimes you'll use eighths, like a 0.16. But for a 0.47, that's essentially 0.5. I hope you guys can see that's close enough. That I'm not rounding here. This is not rounding at all. This is not rounding. I'm putting this to 2.5 because with more exactness, more precision, this would come out to be 2.5. Anywho, we're going to figure out an integer that I can multiply by all 3 of these values and get whole numbers. Now looking at this, I think that I can use 2. I can multiply each of these values by 2 and get whole value or whole numbers. So I get carbon with 3, hydrogen at 5, oxygen at 2. And so I'm simply going to use these numbers as the subscripts in my empirical formula. So my empirical formula is going to be C3H5O2. Again, getting the subscripts from these whole values here, these whole number values. So this is determining empirical formula. Make sure anytime you're trying one of these practices, whether you're just reading through it or if you're working on a worksheet or some sort of sample problems, make sure that you have this portion of your notes out. All right, we're going to move on to finding the molecular formula. So first step, we just determined that the empirical formula for adipic acid is C3H5O2, right? That's what we just did. The molecular mass of adipic acid is 146 grams per mole. What is the molecular formula of adipic acid? And I do want to back up a little here just to make sure you guys are seeing the difference. Empirical formula is the smallest ratio of whole numbers for these subscripts right here. It's the absolute smallest ratio, most reduced ratio possible. But here's the thing. That doesn't mean that's what the molecule actually looks like. Okay, it's all of these ratios have been reduced. The actual molecule could be C6H10O4. They could be C9H15O6. But they're going to be some multiple of 3, 5, and 2. The way we figure out what the molecular formula is we need the molecular mass, which is provided for us right here. The first thing we're going to do in this process is find the formula mass of the empirical formula, the C3H5O2. You guys remember, we simply take the molar mass of each of those elements, multiply by how many of those atoms we have, and we get 73.08. Okay, so we're going to take this 73.08 and we're going to move into part 2. We're going to divide the molecular mass by the mass given by the empirical formula. So remember, the question says that the molecular mass is 146 grams per mole. I'm going to divide that by what I just determined, okay, 73. Oh, but it was 73.08. Again, with increased exactness and precision, that would come out to be, a fairly whole number. But what we're doing here is we're going to divide the molecular mass by the formula mass of the empirical formula. And oops, sorry, I went too fast. And we're gonna get a whole number as a result of this. We're gonna get some whole number. Some number that when we take that number and multiply each of the subscripts in the empirical formula, they'll give 3, in this case, 3 whole numbers, and that's going to be the molecular formula. So, again, we figured out that the ratio is 2. Okay, that's what we figured out by the 146 divided by 73. The ratio is 2. We're going to multiply the empirical formula by this number to get the molecular formula. So we have the empirical formula, C3H5O2. We're going to multiply each of those numbers by 2, and we are going to end up with C6H10O4. Now this is what adipic acid actually looks like. It's C6H10O4. You might be asking, then why do we have empirical formula? Why is that a big deal? What does that give us? What it gives us is a way to functionally analyze something in real life and then figure out what its composition is. This is how quantitative analysis of chemicals happens. They don't spit out, the machine does not give you the molecular formula. What it does is it really gives you the empirical formula. It gives you the empirical formula because that's what can be determined by splitting apart all these molecules and then measuring how many of each element are present. Okay, it's up to us to calculate the molecular formula. Now, so we can go all the way through here determining chemical formulas from mass percent. Okay. So, as a result of being analyzed, here's some results. Okay, we got 18.8% sodium, 29.0% chlorine, 52.2% oxygen. How can you determine the chemical formula? This is going to be one of the larger problems that we see, the multi-step problems that we see in this course. So, start from the beginning. Assume a 100-gram sample. Then, your percent quantities become grams. Right? When we assume the 100-gram sample, it allows us to turn those percentages into grams. Remember, that's what it does for us. So now we have 18.8 grams of sodium, 29.0 grams of chlorine, and 52.2 grams of oxygen. Step 2 is going to be convert those masses into moles. Simply use the molar masses for each of these values, and you'll be able to convert them into moles very, very easily. Again, use the crosshairs. Notice that I've set up these conversion factors using the units. I want you to use the units as well. You're going to see that I'm not going to help you in class unless you're using this procedure. Next up, I notice that these two values are the same and that they are also the smallest molar value. So again, I'm going to need to remember this value as I go to the next step. So I'm going to divide that 0.817 by 0.817 and get 1. Again, do the same thing for chlorine because they have the same molar value, and which means there's going to be a 1-to-1 ratio in terms of number of atoms of sodium and number of atoms of chlorine. When I divide the 3.26 by the 0.817, I get 3.99. And again, I'm not rounding. I'm hoping you see by this point that if we had an infinite amount of precision, this would actually come out to be 4.00. So use these values as the subscripts for your empirical formula. Okay, so we're going to get NaClO4. This is our empirical formula here. Again, we have the ratio of sodium to chlorine is 1-to-1. We have 1 sodium and 1 chlorine atom. The ratio to those two atoms and to oxygen is 4-to-1. So I have 4 oxygens and 1 of each of those other atoms. In the event of the chemical formula is not the same as the empirical formula, because oftentimes it's not, sometimes it is, but oftentimes it's not, you need the molar mass of the desired compound, and then you must compare it to the molar mass of the empirical formula. Divide the given molar mass by the empirical molar mass to get the multiple quantity, and then multiply each subscript in the formula by that multiple quantity. Again, this is what we did in the sample problem just a few slides ago. We're doing the exact same thing here. So, molar mass for the molecular formula. That's what that sub MF means, molecular formula. Molar mass for the molecular formula here is 180 grams per mole. If you use steps, if you would have used steps 1 through 4, you would have found that the empirical formula is CH2O. And by the way, we're looking at a different compound right now. We're not looking at the NaClO4. Okay, we're doing a completely different problem right now. But if we do the same steps, we would figure out that the the molecular formula. We would find out that the empirical formula for whatever this thing is CH2O, and it has a molecular formula with a molar mass of 180 grams per mole. Now I'm going to find the molar mass of the empirical formula. Again, I have 1 carbon, 2 hydrogens, 1 oxygen. You should be able to calculate the mass of that by now. You'll find out that that's 30 grams per mole. Then I'm going to divide the molar mass of the molecular formula by the molar mass of the empirical formula, and it should give me a whole number. 180 divided by 30 is going to be 6. So I'm simply going to multiply the number of carbons by 6. Multiply the number of hydrogens by 6. Multiply the number of oxygens by 6. And so what that ends up being is C6H12O6. And this is our friend glucose. Now, lastly, these are going to be practice problems, and this will be the last slide of this presentation. So go ahead and press pause and take a few minutes and attempt a calculation for each of these. Please press pause now. All right, let's see how we did. Here are your final responses. Please check your answers. Please have any questions on what your mistakes may have been ready to ask. And I will see you next period.